Hello, everyone, and welcome to Module 10, Sorting and Searching Arrays. I'm your professor, Dr. English Dowdell. Now, up to this point, we've been learning how to store and process data using arrays. Arrays are powerful, but when you have a lot of information, finding or organizing, what you need can become tricky. That's where sorting and searching come in. Sorting helps us organize data in a more meaningful order, and the searching helps us locate specific information quickly. Now, these two techniques, they work hand in hand to make programs efficient and user-friendly. If you think about it, you use these techniques every day when you look up a name on your phone or when you search your emails by date. And by the end of this module, you'll be able to explain basic sorting algorithms, describe searching techniques, and model a sorting and searching process using pseudocode. Now, in this lecture, we're going to explore how sorting and searching work conceptually, how they appear in programming, and how to represent them in pseudocode. Now, these skills are going to help you complete both your written reflection this week and milestone 2, system design, which builds on your program's modules. Let's start by thinking about how we deal with information in real life. Now, when you open your phone and you look for a contact name, maybe Jasmine, how would you find it? You probably scroll alphabetically. Okay, that's sorting. Or you might type in Jasmine in the search box. That's searching. Now, in programming, these same concepts are utilized to analyze large data sets. Without sorting and searching, we'd have to dig through data one piece at a time every time. Sorting and searching makes our programs and our lives more organized and more efficient. We'll start with sorting because before you can search effectively, it helps to have your data in some kind of order. Now, sorting is simply arranging data so that it follows a particular pattern. Maybe it's smallest to largest, or maybe A to Z, or earliest to latest. So, sorting means arranging data in a particular order. So imagine we have an array of names, Maria, John, Alice. Now if we sort them alphabetically, we get Alice, John, Maria. That's how sorting is. It takes data that's jumbled and organizes it logically. Now this is important because once your data is sorted, then you can process or find information much faster. Now think about sorting like organizing your playlists or maybe your books. So if your playlist has like hundreds of songs and you arrange them alphabetically, you can find your favorite a lot faster. Or maybe sorting your closet by color or size. You're not changing what you own, just making it a lot easier to navigate. That's exactly what sorting does in a computer program. Let's start with a simple sorting algorithm called bubble sort. Okay, bubble sort compares two items side by side, and if they're in the wrong order, it swaps them. Now, it does this again and again until the list is fully sorted, just like bubbles rising to the top of the glass. So, for example, if we started with 4271, so first we compare 4 and 7. We swap it. Okay. Then we compare 4 to 7. There's no change because it's in the correct order. Then we compare 7 to 1, and then we do a swap. And we continue to do this until no swaps are needed, ending with 1, 2, 4, 7. Now, it's not the fastest method, but it's easy to understand. Okay, so let's look at the pseudocode for a bubble sort. Now the outer loops, they're going to control how many passes we make through the list, and the inner loop is going to be what we use to compare like the neighboring elements. So if one is greater than the next, then they swap places. And then after each pass, the largest value moves to the end, like a bubbling floating to the top. Okay, so let's break this down. So this first line here, this first outer, the four statement here, this loop helps us to keep track on how many passes we've made through the list. Now, each pass pushes the next largest value to the correct position at the end. So, for example, if the array has, say, 10 elements, we need to have up to 9 passes, okay, because the last element doesn't need to be compared anymore. It's already in place. So if you think about this, if you think about it, the loop is really saying, let's make sure we go through the list enough times to move all of the big numbers to the end. So it's taking the length. So again, if the length of the group of numbers or the array is 10, then we're minusing 1. Like I said, we're going to be doing 9 passes because that last element doesn't need to be compared. Okay, this inner loop here, this next step here, this loop goes through the list and compares neighboring pairs of values. Remember the two pairs that are next to each other. So the array J, okay, this is going to be the current value, and then the array J plus 1, this is going to be the next one. So that's your neighboring pairs. So the minus 1 part here makes the loop get shorter every time, okay? Because with every pass, the largest number has already bubbled to the end. So there's no need to check it again. So every time the outer loop runs, the inner loop checks fewer pairs, making the algorithm a little bit more efficient as it goes. Okay. Now this one here, this is the comparison. Okay, so now we're comparing, remember, the current value with the next value. So this checks whether those two neighboring values are out of order. Okay, so if the first value is greater than the second value or the number that follows it, then they're going to be swapped. Okay, so for instance, if we have 4 and we have 2, okay, since 4 is greater than 2, then the algorithm is going to swap them, okay, to 2 and 4. Now this line here, this is actually the swap. This is the step that exchanges the two values. So after each swap, then the larger value is going to move one step closer to the end of the list. And at the end of the first pass, the largest number will always be at the end of the array. Then the algorithm again starts over and does it again for the rest of the list. Now, after the passes, which is the outer loop, and all the comparisons, which is the inner loop, are complete, then the array will be sorted from smallest to largest. Now let's look at another simple method, selection sort. So instead of comparing every pair of values like the bubble sort did, selection sort just looks through the list, finds the smallest item, and then moves it to the front, and then does the swap that way. So for example, if we had 4, 2, 7, 1. So in the first step, it's going to find the smallest, okay, which is the 1. And then it's going to move that to the position 0, okay, or the first position, and then swap whatever was in that position to the previous position, okay. So these two swap because it pulled this, which was the smallest. Okay, so now we look at step 2, which is here, and we say, okay, the next smallest is 2, but that's already in place, so we don't have to do anything. Okay, and then the next is the smallest number is 4. Okay, and so then we move that to the new position. Okay, and we swap those two. Okay, and now we've got a sorted list. So here's the pseudocode for the selection sort. Okay, this algorithm, again, it finds the smallest value and puts it in the correct spot. So it's like sorting, say, a hand of playing cards. You're going to find like the lowest, move it to the front, and then repeat for the rest. Okay, so let's kind of break this down a little bit. So this first line here, again, this is similar to what we had to do with the bubble sort. The loop goes through each position in the array from the first to the last. And I is going to represent the current position, where we want to place the smallest remaining value. The next line here, we assume that the element at position I is going to be the smallest, at least until we find something smaller. So min index keeps track of the position of the smallest value that we've seen so far. So this is like saying, right now, I think the smallest value is at this spot, unless I find something smaller, as I look through the rest. Okay, this next one here, this is your inner loop, okay, like we did before. So now we use another variable j, okay, to check every element after I. Okay, we compare each element to the one at min index. Okay, so for example, if I is equal to 0, okay, then j is going to start at position 1, okay, and then go to the end of the array. Now, this step here, this is our comparison where we're going to find the smallest value. This line is going to check if the current element, which is the array j, is smaller than the one that we think is the smallest so far, okay, which is, remember, our min index, okay? Now, if it's smaller, we found a new minimum. Okay, so then we update our tracker as far as the min index now becomes whatever our new element is, which is j, or our new value, which is j. So basically what this means is that I just found a new smaller value. I'll remember its position for later. Okay, and this process repeats for every remaining element in the list. Then the last one, the last inner loop actually performs the swap. Okay, so after checking each remaining value, the min index now points to the position of the smallest number in the unsorted part of the list. This swap, okay, this swap line here is where we now swap the smallest value into the correct position, I. Okay, and that's the key operation. It locks in one more element into its final sorting position. And then it's going to repeat, so once the swap is done, the first element is in the correct position, and then the algorithm repeats for the next position. I equals now 1. Before was I was 0, now I is 1. But now it ignores everything before that because that part is already sorted. Okay, so everything before the index I is already sorted. Everything after the index I is unsorted. And this process continues until all the elements are sorted. Okay, so let's summarize the two sorting methods that we've discussed. Like I said, we've got the bubble sort. Okay, it repeatedly compares and swaps neighboring values. It's simple, but it takes longer for big lists. Then you have the selection sort, which finds the smallest value and moves it to the correct place. This is easier to follow. It's fewer swaps, but it's still not so efficient on, say, if you have large data sets. But for now, what matters is understanding how they work. That's what I want you to take away from this. And that sorting is the foundation for many more advanced algorithms. Now, here's a few real world examples of sorting that you've probably done today. Okay, sorting emails by date or sender, arranging songs by artists, or sorting maybe your grades or something like that from highest to lowest. Each of these makes it easier to find and process information. So sorting isn't, just a programming task. It's a thinking skill. Now, once your data is sorted, the next natural step is to search for something specific. So sorting, remember, organizes your data. Searching helps you find what you need quickly within the organized structure. So searching means looking for a specific value in a list or collection. So for example, say you have a list of contacts and you want to find John. Okay, you could go through each name one by one until you find him. That's a linear search. Or if the list is already sorted, you could use a binary search to jump around and then find the name faster. Now, a linear search, it's going to check every element one by one until it finds what you're looking for or it reaches the end. So here's the pseudocode for that. Okay, so again, we have here, this is our loop that's going to go through each element in the array as we've been using before. Okay, and what we're doing is we're comparing whatever our target is. So our target, that's the variable of the value that we're trying to find in the array. So like in our previous example, we were looking for John. Okay, so that can be a name, it can be a number. Okay. And what we're doing is we're comparing it, we're checking it against the array item, okay, the current array item to see if it's what we're looking for, okay? If it is, if the target is equal to the array item, then we say that it's found. Okay, return found. Okay, and we keep doing this until we actually find a match. Now, if we don't find a match, okay, then we return not found. Okay, so in the previous example or in this example here, we've got 2, 4, 6, 8, 10, okay, and we're searching for 6. Okay, so the program is going to first check the first one. Is it a match? No. It checks the second one. Is it a match? No. It checks the third one. It's a match. Okay. Now, a linear search is simple and it always works, but it can be slow, again, if you have a huge list. Now, binary search, this is much faster, but it only works if your list is already sorted. Okay, binary search, what it does is it divides the list in half each time until it finds the target. So for example, we've got this array of numbers, okay, and what we're doing is we're searching for the number 9. So what it does is it's going to check the middle, okay, which is 7. Now since 9 is greater than 7, it's going to ignore this left half, okay. Then next middle is going to be 11, okay. Since 9 is smaller than 11, then it's going to ignore the right half. And then what's left is 9. Found it. Okay. It's like searching a dictionary. Okay. You don't check every word in a dictionary. You jump around until you find the right section. Okay. So here's how binary search looks in pseudocode. Okay. So first step is to define the search range. Okay. So low equals 0. So this is going to represent the starting index of the current search range. Initially, it's going to be the first element. And then high, length minus 1, this represents the ending index. Initially, it's going to be the large element. Now together, low and high define the section of the array that we're still searching through. Think of it as two markers pointing at the end of your search area. Okay, the two ends of your search area. You'll keep shrinking that range until you find your target or confirm that, say, it isn't there. Okay, the next step, this while low is greater than or equal to high, this loop continues as long as there's something to search, meaning that your starting index hasn't gone past the ending index. So if low becomes, say, greater than high, then it means that you've looked everywhere and the value isn't in the list. Okay, so the next one is to find the middle of the range. Okay, that's this one here, this line. It finds the middle index between the low and the high. Okay, mid kind of helps you to look right in the middle of the current range. The idea is instead of checking everything, again, we jump straight to the middle and see if the target is before or after that point. Okay, so if low is say 0 and high is 9, okay, then the middle, which would be 0 plus 9 divided by 2 is equal to 4. So that means if we check, say, the fifth element, okay, because remember indexes start, arrays start at index 0. Okay, so we're going to be checking the fifth element, and that's going to give us that middle one. Okay. Now the next line here is to compare the middle value to the target. Okay, so this is the first check. If the value at the middle, okay, is matches our target, okay, then we're done. Okay. The binary search again is designed so that if the target is present, then this condition will eventually be true. Okay, meaning that it's found. Okay, now if it's not, then what we do is we're going to narrow the search range. So if the middle value isn't the target, okay, here, then we decide whether we want to search the left half or the right half of the list. Okay, so if the target is greater, remember when I did the example in the previous slide, if the target is greater, okay, meaning if the middle value is smaller than the target, okay, that means that the target must be in the right half of the array. Okay, so then we'll move our marker up one spot after the mid, and then everything before the mid is ignored because it's too small. Okay, but if the target is smaller, okay, meaning that the middle value is larger, okay, than then the target must be in the left half. Okay, so then we move our high marker down one spot before mid, and that everything after mid is going to be ignored because it's too large. Okay, so each time you do this, you throw away half of the remaining list, like we saw in the example in the previous slide. So this loop keeps repeating, okay, calculating a new middle position, okay, comparing it to the target, and then eliminating half of what's left. And eventually, one of two things is going to happen. Either you're going to find that the target is found, okay, or the range is going to become empty, okay, and then it's going to return not found, okay. So let's compare the two concepts. So sorting is where we organize our data. So example is we alphabetize the contact names. And again, this is requiring sorting. Okay, searching is when we're looking to find specific data. So for instance, looking up a contact by first name. And as we saw in our two examples, sometimes depending on the type of searching that we're doing, we may or may not need to have that sorting done. So think about it like this. Sorting prepares the data, and then searching uses that data efficiently. Okay, so imagine you have a program that stores 10 book titles in an array. Okay, how would you write the pseudocode to search for a specific title? Okay, so what I want you to do is I want you to take the time, think about what would your input be? Okay, what steps would the program take? And what would your outlook or your output look like? Okay, this is exactly the kind of thinking that's going to help you to develop logical flow in your program. Okay, so take a moment to do that. Pause this video. Okay, so now let's look at this together. Okay, so the first step, the program is going to create that array called book titles that's going to hold 10 books. Okay. We're going to use a loop, okay, that's going to ask the user to type in each title one at a time. Okay. So after this step, the program is going to have a list that might have content that's like The Hobbit, 1984, Pride and Prejudice, Moby Dick, Hamlet, The Great Gatsby, so on and so forth, Dracula. It's going to have a list of 10 book titles. Okay, this is the collection of books that the program is going to search through. Okay, the next step is that the program is going to ask the user to enter the title that they want to find. Okay, now this title is stored in the variable search title. Okay, so for example, maybe the user might be looking for the book Moby Dick. Next, the pseudocode is going to use a variable called found, and it's going to set it initially to false at the start. Okay, this is going to act as our flag. It's going to help the program remember whether the book has been found or not. If the program finds a match, then it'll change found to true. Okay, but if it doesn't, it's going to keep it at false. Now the program goes through each book title in the list one at a time using a for loop. Okay, and so for each item in the array, it's going to check whether the current title equals the search title. We saw this in the previous slide. If the match is found, then the program displays a message such as, book found at position 4, something like that. And then it changes found to true and then exits the loop early since there's no need to keep searching. If it goes through the entire list and say doesn't find a match, then the flag is going to stay false. And then finally, after the loop ends, the program is going to check the value of found. If found is equal to true, then it already displayed the success message. But if found is equal to false, then it means that the title wasn't found, so then it's going to print book not found in the list. Now, why does this work? It uses the approach called linear search, which we learned about a few slides ago, because it searches through the list in a straight line, from the first item to the last. It's easy to write and understand, but if the list gets really long, like I mentioned before, it can take some time to search since the program might have to check every single item. Now, this is similar to how you might look for a book on an unsorted shelf. Okay, you might start at one end and then check each book's title until you find the one that you want. Now, if the books were alphabetized, okay, then we could use that faster method that we just learned about, which is the binary search, okay? But for shorter lists, the simple linear search, works just fine. Okay, so now let's connect this to your milestone 2 assignment, okay, which is system design plan. So you're creating a system with modules, okay, such as a register, cancel, view schedule, okay, to accommodate the different tasks that you need to do for this system. Okay, sorting and searching are going to likely be part of how these modules work. I'll say, for example, in your register model, you might search to see if a student participant is already enrolled in a class. Okay, your cancel module might search for the correct record to be removed. And then your view schedule module might sort the schedule by course name or maybe by date. Now, these are practical ways sorting and searching can appear in your programming logic. Okay, now let's look at an example of the IPO chart for maybe the view schedule module. Okay, so for input, it's going to take the student ID. For the process, it's going to search for the student's courses and then sort by course name. And then the output is going to be to display the sorted schedule. Okay, so this is how you're going to connect your logic to your system design. Each module should clearly show what information it receives, okay, what process it performs, and then what it actually produces. Now, sorting and searching, they aren't just classroom ideas, okay? They're used in nearly every modern system. When you Google something, the engine searches millions of pages and sorts, um, results by relevance. Okay. When you shop online, results are sorted by price or popularity or rating. Even your library's card catalog or catalog system searches for books and sorts them alphabetically or by subject. Now, these examples show just how critical these concepts that we've been talking about are to efficient system design. Now, you have two assignments this week. One is a sorting and searching reflection. So, you're going to write a 2 to 3 paragraph explaining the difference between sorting and searching. I want you to include one real life example of each, like sorting your playlist or searching your phone contacts. And then the second is to work on milestone 2, the system design. Okay, so you're going to create your hierarchy chart and separate IPO charts for each main module: register, cancel, and view schedule. Now, both assignments build directly on the concepts from this lecture. Okay, now before I wrap it up, let's review some of the key points. Okay, sorting organizes data into a logical order. Searching helps locate data efficiently. Now, sorting and searching, they make programs more usable and responsive. And these processes appear in real-world systems and in your Milestone 2 project. Okay, so that's it for this module. So now you understand the basics of sorting and searching, which are two fundamental operations that make programs very powerful. I've also provided like some additional resources in the module course room for you to be able to read through and review. Now, be sure to complete your reflection and your system design milestone. Now, next week, we're going to explore how to store and retrieve data from files, which will make your program even more functional. So thank you and have a good week.